Given an object in harmonic motion described by the function x of t is equal to a sine omega t, what is the maximum speed of the object? That's kind of an interesting question. I don't know if that's something we can just plug into that to find out, but I think we'll be able to use the result of the math example that's right before this one, combined with kind of an analysis of this function to reason our way towards an answer. And what I'd like to start with is a graph of this function. So I'm going to sketch a graph here of what I think looks like a sine function that depends on time. I'm not sure if I left enough space there. I think the thing about sketching, though, is it doesn't have to be perfect. The way I'd like to look at this, I mean, this is x versus t of a sine omega t. And if I imagine what this is actually describing, this is describing harmonic motion. So there's an object that this describes. Maybe it's a mass on a spring. Maybe it's something hanging from the end of a string like in a pendulum, and it's swinging back and forth. If it's a mass from the spring, it's bouncing up and down. And it makes sense that the maximum speed of that object that is going back and forth or bouncing up and down would probably happen about halfway between the farthest extent of its motion in either direction. Well, the farthest extent of motion in either direction really corresponds to the amplitude a on the vertical x-axis and minus a down here on the same axes. And so the places where the speed is maximum would be at the points halfway in between, which would correspond to like this spot right here, this spot right here. And really, harmonic motion never really stops. I've just drawn one period of this one, so there'd be more and more spots where it would go through that maximum speed. Let me look at this one right here a little bit more closely. When we're close to that spot, it could be argued that t is small, because this spot corresponds to t is equal to 0, which is basically as small as t is going to get. So t is small. Maybe you could even say that whatever omega is, whatever the angular frequency of this motion is, omega times t would also be small if you're getting close to 0. So if omega t is small, wouldn't that imply that sine of omega t is approximately equal to just omega t, which would mean that x of t is at very small values of time is approximately equal to a times omega t. Or maybe the way I could interpret this is to say this is a times omega times t. Well, let's compare this function to a function that represents just constant speed, right? A function like that would be x of t is equal to v times t. So this function I've gotten to here really is describing an object that is moving with a speed equal to a times omega. I'd like to, if I were to draw a graph of this is just a line, right? So that may help us to picture exactly what's being said here. Is that line I think would look like this, because we said that this is approximately equal to really the function that's given, the x of t is equal to a sine omega t in the original slide when t is close to 0. And that's true because this line is really close to that sine function. But as you get farther away from 0, they start to move apart. And at some point, the line just keeps right on going up. And of course, the sine function is going to do its kind of bouncing up and down thing and keep doing that. So the farther out you get in time, the more different these two functions get. But it makes sense that maybe the speed described by this linear function corresponds to the speed of the sine function right at t equals 0, which is what we originally said is going to be the maximum speed. So therefore, I'd like to conclude that the maximum speed should be equal to a omega. In other words, amplitude times angular frequency. Let's go ahead and check that answer, and you can see that there's a similar looking graph there that we used and the result.